So dear students, in this video we are going to discuss, okay, I just want to correct what I have I've mistakenly said one thing to you about magnetic force, and that is magnetic force and that is I told you that a current carrying conductor experiences a force in a magnetic field. A current carrying conductor experiences a force in a magnetic field, and the value of the force was I L cross B, and I have given you a rule that gives me the direction of each of the vector in the given formula, and they are force, length and magnetic field. So basically, if you see here, the magnetic field is going inside the plane of the paper, and suppose you have a current carrying conductor of length L, the current is in this direction, length L, and the current is in this direction. So the direction of the current is the direction of the length itself. So what I told you was, if this way, I told you, if this was the direction of the current and if it was the direction of magnetic field, then the direction of the forces, so I can easily identify using my left hand Fleming's rule. So what I told you was earlier, this was the direction of the current. This finger gives you the direction of the current, and that was wrong. So actually this direction will give me the direction of the current, and this direction will give me the direction of magnetic field, and the thumb will give you the direction of the net force. So in this case, current is going in this direction. For this wire, current is going in this direction, so that is the direction of the current, which is basically the length. And magnetic field is going inside, so this is the direction of current, and magnetic field is going inside, so this particular thumb will give me the direction of the force. So this is the direction of the magnetic force in this particular relation. This is true even when for a single charge. Suppose you have a single charge moving with some velocity v, then if it is a magnetic field, it is in the magnetic field, if the charge is in the magnetic field and if it is moving, then the force experienced by the charge will be q v cross b. So the charge will experience the force only when it has some velocity. So velocity is given by this finger and magnetic field is given by this finger. In this case it is downward. Cross give me the show me the direction downward, and v velocity in this direction, and this particular finger will give me the direction of the force, magnetic force, which is this one. Now in the same manner, what I want to do right now is motion of a charge in magnetic field, which means how a charge behaves in a magnetic field. So before that, what I want to tell you is a charge experiences a force of this much when moving in a magnetic field. So let us take, if this is my velocity v of a charge q, and if it is a magnetic field which is going inside the plane of the paper, then it will experience as a force, and the direction of the force will be given by thumb rule. So not thumb rule, left and Fleming's rule, which is this is the direction of magnetic field, this is the direction of velocity, so this thumb will give me the direction of the force, which is in this direction. So this is my force, this force is this one, so this force is this one, which is directed upward. Now this can also be seen in this way, by simply a rule is there, and that is my left hand rule. That is v cross b is nothing but you have to bend your, let's say, let me tell you, this is the direction of velocity v, and okay, magnetic field, okay, that is right hand rule, this is known as right hand rule. So this is the direction of velocity, so make your 4 fingers parallel to the velocity and bend it towards the magnetic field, because magnetic field is downward, velocity is in this direction, so you have to bend it towards the direction of the magnetic field. Then your thumb will give me the direction of the force. Since this is the direction of magnetic field which is going inside, and this is the direction of velocity parallel to the paper, so you have to bend your 4 fingers parallel to the plane of the paper towards the velocity, and bend it towards the magnetic field, which is your pen, and the thumb, the left thumb, will give me the direction of the force, which is this direction. So it can also be seen by this particular rule, which is known as right hand rule. Right hand rule. The same thing I am going to apply in this particular case. Okay, you have a magnetic field, let us say, which is going inward, which is going inward, which is going inward, which is going inward, and suppose you have a charge particle q with certain velocity v, which is perpendicular to this magnetic field, which is going moving on a plane c. So the charge has a velocity v and magnetic field has a magnitude of b, which is going inward. Velocity is in a plane of the paper, so force will be q v cross b. So force will be equals to q vb sin theta. Vb sin theta is the cross product of v and b. Now since in this case velocity is in the plane of the paper and magnetic field is going inward, that means theta is 90 degree. Angle between velocity and magnetic field is 90 degree in this case. So your force will be simply qvb. Magnetic force is qvb, because theta is 90 degree, so sin theta is 1. So let us see what happened. Since velocity is in this direction at this particular point and magnetic field is going inward, so what will be the direction of the force? Let us see. The direction of the force will be, so parallel, this is the direction of velocity, so I have to make my 4 fingers towards the velocity v. This is the direction of the velocity, so I have to make my 4 fingers parallel to the velocity and bend it towards the magnetic field, because magnetic field is inward. That means the thumb will give me the direction of the force. So thumb will give me the direction of the force. So force is in this direction. This force, qvb force, is in this direction. Magnetic force is in this direction. And again, after some time, this particular charged particle will, let us take, reach at this point. Let us see, it will reach at this point, and at this point it has a velocity towards this direction. This is the velocity. Then in this case, let us see what will happen. The force will be again, if I bend my 4 fingers from velocity direction to the magnetic field direction, so the thumb will give me the direction of the force. So force will be towards this direction. The force will be towards this direction. So after some time this charged particle will reach here. So what is happening in this case is, uh, as the charged particle is moving, the force will be towards this direction and velocity will be towards this direction. After some time the charged particle will reach here, the force will be in this direction and velocity will be in this direction. This is my force, this is my force, this is my velocity, this is my... After some time it will reach here, velocity will be in this direction and the force will be in this direction. After some time the charged particle will reach here, the velocity will be in this direction and the force will be in this direction. So if you look closely, this particular dots will gives you a circular trajectory, because at each point the force will be velocity will be tangential and the force will be towards the center. At each point of the trajectory, the velocity will be tangential and the force will be towards the center. At each point on the trajectory, the velocity is tangential and the force will be towards the center of the paper. So actually what is happening, if a charged particle is moving in a magnetic field, it is making a circular trajectory of radius, let us take r. So let us take, if the circular trajectory has a radius of r, that means if a charged particle moves with a uniform velocity, in a magnetic field, then it will make a circular trajectory. So let us see what is happening. So the charged particle is moving in a magnetic field, and the angle between the velocity and the magnetic field is 90 degree. So it will make a circular trajectory of radius r. Now since this force is towards the center of the trajectory, circular trajectory, so this force is also known as this force, which is a magnetic force of course, and it is also known as your centripetal force in this case. That means magnetic force will play the role of the centripetal force in this case to move the charged particle in a circular trajectory. And we know for a centripetal force, the value of the force will be mv square by r. This is the value of the centripetal force, and the centripetal force role is playing by our magnetic force, which is qvb, of course. So this is a centripetal force, this is a magnetic force. So in this case the role of the centripetal force is playing by the magnetic force. So you can easily calculate the value of the radius of the trajectory in which this charged particle will move. So mv square by qvb is the radius of the circular trajectory made by the charged particle. So let us quickly revise what we did here. So what we did here is, a charged particle moving in a magnetic field will make a circular trajectory of radius r, and in a circular trajectory, the circular trajectory or a circular uniform motion, if there is such motion, there must be some centripetal force involving. A centripetal force will move this charged particle in a circular trajectory. For a circular trajectory to happen, there must be a centripetal force there. So what is centripetal force? Which force is playing the role of the centripetal force? For example, if Earth is revolving around the Sun, the centripetal force role is played by the gravitational force. So similar manner, in this case, the role of the centripetal force is played by the magnetic force. And when the charged particle moves in a circular trajectory, the value of the radius of the circular trajectory depends upon the velocity of the charged particle and the magnetic field. mv square by qv. Okay, v cancels, 1v and 1v cancels, so it is mv by qv. So this radius of the trajectory depends upon the velocity of the charged particle, the magnetic field in which it is moving, the mass of the charged particle, and of course the magnitude of the charged particle. So a charged particle moving in a Magnetic field will produce a circular trajectory of this much of radius. So this is it for today.